So as John said, my name's David. I'm going to talk about stress relaxation cracking in superalloys for power plant construction. Superalloys are not normally used for power plant construction, and this is a newer prospective application due to the efficiency gains from increasing the temperature of power plants. I like to point out this project is part of the NSF IUCRC SimJC Center, and it's sponsored by the Babcock and Wilcox company, the Power Generation Group, more specifically. So I'm going to talk a little bit about a testing approach I've been trying to come up with for relaxation cracking, because relaxation cracking really is a creep-related phenomenon. And so after that, I'll explain the first round of testing. So first, let's go into the motivation of this. And so this just simply explains how we arrive at these steam conditions termed advanced, ultra, supercritical. And so the efficiency gains from increasing the temperature help reduce CO2 production. And the problem, though, is that this jump from ultra supercritical to advanced ultra supercritical, you start to need superalloys in more and more places throughout the power plant, mainly main header pipes. So that's the goal here is to evaluate superalloys for main header pipes for AUSC power plants. The critical term here has to do with the triple point of water when you get to a supercritical fluid. Anyway, so the materials conditions which are desired for AUSC applications here is rupture life of 100,000 hours at 760 C and 100 MPa. So when you put this point on here, you see you pretty much narrowed it down to only precipitation strengthened nickel-based alloys. So the two leading candidates are alloy 740, alloy 282. Alloy 282 actually wasn't designed for this application. 740 was, and so it has advantages in terms of fire site corrosion resistance. This is a little bit of background about 740H as a leading candidate. I'd spend a little time on this. So the starting point for the development of 740H was mnemonic 263. Is I think an older aerospace alloy, and so this is the composition of alloy 740. Important things to note are the low molybdenum, which helps with the fire site corrosion resistance I mentioned. I think molybdenum sulfides are susceptible to liquating at these temperatures. So there's also a little bit of niobium, which will participate in the gamma prime formation. I think is causing some problems for this alloy. This picture here, though, is a big extrusion of actually alloy 740H. I think one of the biggest extrusions of an alloy this sort of composition. And this pipe has been sectioned and welded back together with great success, actually. So this picture is a thick section weld through that pipe. It's 3 inches thick. This is a 10-degree included angle, and it's single pass about 2/3 of the way. And this has been successfully post-weld heat treated, which is pretty encouraging. The problem, though, is that the post-weld heat treatment that is desired is simply an aging treatment. So it'd be ideal to get away with only an aging treatment and then put this thing in service. But when you're only aging, you're not relieving very much stress because you're forming all this gamma prime, and so then you're kind of setting yourself up for a relaxation cracking problem. And so, as I mentioned, we would rather not anneal and then age these main header pipes because this is for power plant construction. And so the post-weld heat treatment temperature and the service temperature are almost exactly the same. So you're never going to fully relieve any residual stress because you have all this gamma prime precipitation. And so then when you heat this back up and you begin service, you have an overlap of creep and residual stress. And so relaxation cracking I would almost term as residual stress accelerated creep. And the microstructural situation here is that in the heat affected zone after welding, you presume most of the gamma prime would be dissolved, and so you'd simply have your grain boundary structure. And so then as you age, you form gamma prime, or reform gamma prime, mainly within the grain interiors. And so the boundaries are going to be weaker relative to the interiors, especially if you have gamma prime forming elements, either making large boundary gamma prime or in some other precipitating phase. And so now any stress relaxation or creep strain has to be accommodated by these boundaries, which so is a reduced area, and eventually in service you would have cracking on intergranularly. And so you can imagine also if the grains were larger, there would be less grain boundary area, and this the alloy would be more susceptible to cracking, which is leading into unfortunately the situation you want for creep resistance is larger grains, but also make you more susceptible to a phenomenon like relaxation cracking. So as a creep-based phenomenon, there are different tests we've tried to do, and especially in the glebal. But today I want to talk about a test which moves away from the glebal, and it's based on a compact tension sample. And so these authors, Mark Tursky was a PhD student under Professor Withers, and he was investigating this similar cracking phenomena in 316H stainless steel. And so I really liked his testing approach because it's entirely self-restrained and dependent. The loading is dependent entirely on the material. So what you do is you take a standard compact tension sample and pre-strain it in compression, and then you yield a little bit of material behind the notch root, and then you unload the sample. So now the part which you yielded is in a tensile residual stress. And so you simply put this sample in the furnace, unload it, and let that stress relax, and you arrive at an accelerated creep test. And so the sample geometry, of course, is extremely common. And in this work, there's a lot of characterization of the residual strain. So this is an example of that. They created a 3D finite element model, and with a small gauge section of high energy X-rays, we're able to observe residual strain very similar to what they predicted in their modeling. So results from this initial work in alloy 316H, this testing was done at 550 C for about 4,500 hours, and these authors were actually able to predict the creep damage with some additional modeling they did. But I just want to focus on the microstructures here. This is half of the thickness of the sample, so this is the mid-thickness plane. And you can see that for a pretty consistent portion beyond a quarter of the thickness here, so which would extend another quarter to be over half the thickness of the sample, there's pretty consistent crack depth. And so what I wanted to do was extend this approach to much thinner samples because, mainly because I had a whole bunch of half-inch thick plate. And so my approach there was to start by making an abacus model, just a simple elastic plastic model, and lining it up with Mark Tursky's model because I knew he had validated that his model was accurate. So I did that, and those are the red lines, and then it was real easy to start changing the geometry, and so I made the sample smaller this way, and I reduced the thickness to 40% of the original thickness, and was still able to have a pretty similar stress and strain profile immediately behind the notch. And So there are actually two sets of lines here, one from the mid-thickness plane and one from the quarter-thickness plane. And since they lie pretty much on top of each other, that means the middle half of the sample has a uniform distribution of residual stress and strain. This is just an illustration of that. You can see the profile here is pretty consistent. It's not some very narrow peak in the middle. So another advantage of making the sample so thin, 40% of the original thickness, is that now I can fit it in the glebule. And so that's great because I can make virtually any microstructure I want in this area, which I'm going to yield and subsequently creep test. So the big picture game plan for me, or the ultimate goal, is to test the creep response of the relaxation cracking response of simulated heat affected zones. But of course there are a couple rounds of testing before we get there. So round one, which I'm going to discuss the results of round one real soon, was simply to look at a range of microstructural conditions. First of all, to make sure that there would be cracking, and hopefully this cracking will correspond with the right microstructure. Based on the results of round one, I determined that I need to take a step back with round two and look at the various degrees of pre-straining, maybe not pre-strain as much, or try to slow down the cracking I observed. See, the heat-affected zone simulation will be done like this. I've been trying to build a potential drop system to monitor crack growth, so I'll explain that really briefly. And what I'm mostly going to talk about are the results of this first round one test. So there were no cracking in a couple of the alloys which start out without any precipitates. There was minor cracking in this 740H, which had been aged for 10,000 hours. And there's some pretty severe cracking in this 740H base metal sample. And you will see why. So the problem, though, and the motivation for making round two have reduced pre-straining at lower temperatures, that I think all the cracking occurred sometime within the first 130 hours. And I'm not real sure about that because I spent those first 130 hours tweaking this and that in the potential drop system. The potential drop system looks like this if you're not familiar. So I have a current daisy chain through all these samples, and so you simply take a measurement, a reference measurement, and this is actually determined to be one of the better locations to make your reference measurement. And so the actual crack growth measurement, of course, happens here, and you simply compare these voltages as you go. The basic principle is that you have a constant current power supply, which is this horizontal line, and so then all these leads, the reference and measurement leads from all the samples, go into a multiplexer, which basically, based on the program in LabVIEW, will select the channel and write the channel, and select the next channel. So then you only need one amplifier and one data ACK. Currently I'm working on updating this to have a polarity switching feature, so Seebeck effects can be accommodated for, because if cracking is going to happen so quickly, now I need to worry about the initial heat up, and I need to be able to subtract out those changes in voltage with temperature. But anyway, let's go on to the fun stuff, the microstructures here. So this is the initial condition for round one testing. So I have these 4 different situations. I have alloy 230. Alloy 230 is solid solution, or you may say carbide strengthened alloy. It has no gamma prime. It has 14 weight percent tungsten. It's the most remarkable feature of this composition. Here is alloy 617 is a very low gamma prime fraction, and it started out in an annealed condition. So alloy 740H is about 20% gamma prime, and you can see here it clearly has the largest grain size on the right. On the left, this sample was aged for 10,000 hours. You can see some small recrystallized grains. So this alloy had a much coarser gamma prime and a bimodal distribution of grain size. So here's an example of the precipitation. There's simply tons of carbides in alloy 230. Alloy 617 start out without any gamma prime. The AH740 has a really uniform distribution of very fine gamma prime, and in the 740H pre-aged for 10,000 hours, of course they're very coarse cuboidal gamma prime. And so now the testing was done at 760C. So just take a look at a TTT diagram for reference. So pretty much anywhere in this 400-degree temperature range, it's certainly going to form or coarsen gamma prime. That's going to be the main reaction. So this is what was observed after 1,500 hours at a really low magnification. There's no cracking was found in 230 or 617. The 617, which I thought was annealed, certainly wasn't homogenized. And these I think are a dendritic structure, and there's no precipitation in those whiter areas. I'll show you that. There's some minor cracking in the pre-aged 740H, and a huge amount of cracking in the simply post-load heat-treated aged base metal 740H condition, and which I would say, at least for me going into this, was pretty expected because the initial grain size is so huge. This is simply a closer look at this cracking and the microstructures I just mentioned before. So this is a much clearer look at the bimodal grain size in 740H, which would have allowed more stress to be accommodated. I guess an important thing to note is that this cracking is intergranular, which is the kind of cracking I wanted to generate. So this is where it gets really interesting, is in the precipitation. This is the precipitation I would expect in 617. The questions that are arising for me, though, have to do with alloy 740H. So if you've been following my work or Dan Bicchetti's work, you may know that there is discontinuous precipitation reactions where gamma prime forms perpendicular to a grain boundary, and the coarsening discontinuous gamma prime forms at the expense of the regular gamma prime. And I wish I could say that this crack was formed by that, but I'm not sure I can. And I want to, before I move on, point out that this is a similar surface breaking crack. It's important to note these are surface breaking crack in the 10,000 hour aged 740H, and they're very clearly precipitates adjacent to and all the way into this grain boundary. The interesting feature, though, is that the gamma prime dissolution seems to be more related to simply the presence of a free surface or exposure to environment, and for some reason only in the 740H, which was aged only for 4 hours, and so within this 10,000 hours, the gamma prime must be stabilized beyond the point where it can dissolve in air. But I haven't really investigated this too much, and I need to. I suspect that this situation is a combination of discontinuous precipitation and the exposure to the environment. So the so what from this, my big conclusion is that it worked. So the thinner sample worked, and which is really what I set out to figure out in round one. And so not only did cracking occur, but the test method was sensitive to different microstructures. And so, as I tried to step through with you, the grain size and the precipitate presence were clearly the controlling factors. Unfortunately, I didn't observe the cracking the potential drop data, which makes me think it occurred in the first 130 hours when I was still trying to get it set up. And so in that case, cracking pretty much occurred too quickly, and it's more like a, an on-heating cracking mechanism, such as strain-age cracking. So in order to slow that down, I want to change the pre-strain, which I don't think will affect the rate of cracking, but reducing the temperature certainly will. In order to make sure I detect cracking early on, I'm going to add a polarity switching feature. And as I've been saying, the point of round 2 is to moderate the creep rate, and that'll be done with 740H only. And so the real testing, or the real results when we can start to compare alloys, happens in round 3 with simulated heat affected zones. So this is these 4 AUSC type alloys. So that's what I have. Thank you, and I welcome any questions.